Hello, Math Study students. Let's take a look at our 4.4 notes. We're going to be studying exponential models. So let's first talk about what an exponential function is. Well, an exponential function is a function where the independent variable, usually that's going to be the x variable, or the independent variable is the exponent, or at least can be found in the exponent. Sometimes that exponent might be an expression in terms of x, but in either case, an exponential function, the independent variable will always be in the exponent or be involved in the power. So here's some examples of some exponential functions. If you look at each one of these, where do you find x? X will be found in the exponent. Okay, so we'll be studying the graphs of these functions in just a minute, but let's first talk about kind of a general equation for an exponential function. It looks like this. F of x is equal to k times a to the x plus c, where now a is going to be, we'll call that the base of our function, okay, and that base will always belong to the set of positive rational numbers. Remember, we use this capital Q to represent the set of rational numbers. And so a, your base of your exponential function, will always be a positive rational function. Also, in this equation, k cannot be equal to 0. I think that's obvious. If k were 0, then this whole term would zero out and you just have a constant function. And then also a, the base, cannot be equal to 1, because if a were 1, raise 1 to any power and you would always get 1, then it's not an exponential function anymore. It would be a constant function. Okay, so we're going to start talking about the graphs of these exponential functions. And what we're going to do is compare several examples to this. We might want to think of this like a parent function. Let's consider the graph of y equals 2 to the x, which is shown here. And what we'll do is we'll type each of these equations into a calculator and compare its graph to this graph. But before we do that, I just want you to take note of a couple of things. Let's take note of two things. First of all, I want you to take a look at the y-intercept. The y-intercept will be useful when we go to sketch these graphs. In this case, our y-intercept is the point 0, 1. And I think that's obvious because what happens when you put 0 in for x? Well, 2 to the 0 power is equal to 1. So we'll always graph the y-intercept. And the other thing that will be helpful is to look at the horizontal asymptote. Okay, these exponential functions will always have a horizontal asymptote. In this parent function, the horizontal asymptote is the x-axis. And I think you can see why. Because as these x values get smaller and smaller and smaller, as they get more and more negative, let's just look at some examples. Like, for example, 2 to the negative first power is equal to 1/2. Okay, 2 to the negative second power is equal to, that would be 1 over 2 squared, or 1/4. 2 to the negative third power is equal to 1/8. You can see how these numbers are, these y values are getting smaller and smaller and smaller and smaller, but they're never going to get to 0, because is there any number that we could put in for x here that would create a 0? And the answer to that is no. So these exponential functions will always have a horizontal asymptote, and we'll use that horizontal asymptote along with the y-intercept and just the general shape of an exponential function to sketch their graphs. Okay, so these first two graphs we're going to look at, we're going to compare what happens to the function when the base is bigger than 1, or when the base falls between 0 and 1. Remember, that base of a is always going to be a positive rational number, but the graph will look different depending on if that positive rational number is bigger than 1 or if it falls between 0 and 1. So first of all, let's just re-sketch here, and we're going to sketch teeny tiny graphs here. The graph of y equals 2 to the x, remember it goes through the point 0, 1, and it has a horizontal asymptote at the x-axis, so it looks like that. So what I want you to notice is that when a is bigger than 1, then you're going to be looking at a exponential function whose graph is increasing. Okay? Now, what I want you to do is actually take the time to stop the video and type these in, because I'll sketch the graphs, but they'll look better on your calculator. So if you wouldn't mind stopping the video now and typing in this function, and then start it again. Okay, so the graph of y equals 1/2 to the x power looks like, if you look at your calculator, it's going to look something like this. Okay, it's going to have the same y-intercept as y equals 2 to the x, but in this case, the graph looks like this. Okay, whoops, it should go right through that point. Okay, so when a falls between 0 and 1, then you'll see that that is the graph of an exponential function that is decreasing. And we'll look at some models here at the end of the lesson where you see examples of those types of functions. Okay, the next thing I want to look at is what happens when we have a coefficient that's bigger than 1 and where that absolute value could be bigger than 1 or it could be smaller than 1. So if you could type in this function, y equals 3 times 2 to the x, and when you do, oops, what's going to happen is the y-intercept isn't going to be at 0, 1 anymore. It's going to be at 0, 3. Okay, and so the graph will look something like this. Okay, so what happens when you multiply this function by a k value that's bigger than 1 is the graph will be vertically stretched. So there'll be a vertical stretch. And so it might not surprise you when you type in this function or this equation, y equals 1/3 2 to the x. When that k value is less than 1, that's going to be a vertical compression. So in this case, the y-intercept will be at 0, 1/3. So the graph looks something, whoops, like that. Asymptote didn't change. So that's going to be a vertical compression. Okay. Now, what about if k is negative? Okay, well, it shouldn't surprise you that if I take a function, take its output value, 2 to the x would be its output value. If I multiply it by -1, we're going to have the opposite y values that we would have if k were positive. So what the effect that has is it flips the graph upside down. So it's going to be a reflection of this graph. It's going to be, whoops, it's going to be a reflection in the x-axis. It's just going to get flipped upside down. So that means that its y-intercept instead of +1 is going to be at -1. And the graph will still have the x-axis as a horizontal asymptote on the left, so it'll look something like that. All right, so if k is less than 0, then that means the graph will be a reflection in the x-axis, or another way to state that is that the graph will just flip upside down. Okay, now, how about this one? What if we take that parent function 2 to the x and add 3 to every output value? Well, if every y value is going to be increased by 3, obviously the effect that's going to have is it's going to shift the graph up 3 units. So what I'm going to do, and again, you can type this in and take a look at it. What I'm going to do first is I'm going to sketch a new horizontal asymptote. Remember, on the parent function, the horizontal asymptote is the x-axis, but here we're shifting up 3 units, so we have a new horizontal asymptote. I'm just going to make it in red. Okay, so that's our new horizontal asymptote. Also, that y-intercept has been shifted up 3 units, so now the graph is going to go through the point 0, 4, so it will look something like that. Okay, so what happens when we have a c value that's bigger than 0? Well, that means our graph will be shifted up. So we'll shift it up, and so obviously I think you can figure out what's going to happen when c is less than 0. That's where all the y values will be decreased by 4, so that's going to shift down. So to sketch that, let's see, I'm going to draw the new horizontal asymptote. So instead of it being at the y-axis, it's going to be at -4. So there's our new horizontal asymptote, okay? And that y-intercept that was at 0, 1 has been shifted down 4 units. So it's going to be at -3. And so the graph would look something like that. Okay, so when C is negative, that means that the graph will be shifted down. So we will shift down, okay? And then last but not least is I want you to take a look at what happens when there's a negative sign in front of the x value, okay? So when we take opposite x values, if you think about the coordinate plane, well, where do you find opposite x values? You would find opposite x values on the opposite side of the y-axis. In other words, what's going to happen when you put a negative sign out in front of x is the graph will be reflected in the y-axis. So it's going to end up looking just like this graph, okay? This graph was also a reflection in the y-axis. So it will look like, it'll have a y-intercept of +1, a horizontal asymptote at the x-axis, but it will be a reflection, okay? So this will be a reflection in the y-axis, or another way that we can say that is it will, I guess we can just say it flips sideways. Flip sideways. That's not very technical. Okay. So we can generalize this whole chart in just a couple of statements here. In general, the graph of y equals k times a to the x plus c, where a is an element of, let's see, for some reason the computer didn't recognize that symbol, put a capital Q there, where a is a positive rational number, and where k is not equal to 0 and a is not equal to 1. In general, a graph, an exponential function of this form, will have a horizontal asymptote at the line y equals c, and will pass through the point 0, k plus c. In other words, this is where we'll find the y-intercept. Okay, so that's really all you need to remember, is when you go to sketch the graph, find the horizontal asymptote by just looking at the equation y equals c, and then add k, the coefficient of the a to the x term, add it to c, and that will tell you where your y-intercept is. All right, so let's get some practice sketching the graphs of some exponential functions. But before we do, let's make a list of what would be required if you're asked to sketch an exponential function. First of all, you need to draw and label the axes. Make sure we know the x-axis and the y-axis. Secondly, we're going to draw and label the y-intercept. So we'll know what that is. And lastly, draw the horizontal asymptote. So we'll start with the y-intercept and the horizontal asymptote, and then we'll just use our knowledge of the general shape of an exponential function to get it to sketch it. Okay, so let's take a look at this first example. F of x equals 2 times 3 to the x plus c. So first of all, notice that that base is a number bigger than 1. Also, the coefficient is positive, so we know that the general shape is an increasing function. So we know it's going to look something like that. So let's get a sketch by starting with the x and y axes. Now, when you draw these axes, remember the y-intercept is going to be at 2 plus 5, or at 7. So make sure you have enough room for that. So here's our x-axis, and then the y-axis. 1, 2, 3, 4, 5, 6, 7. Okay, so let's start by sketching the the horizontal asymptote. And remember, the horizontal asymptote will be the line y equals c. So the horizontal asymptote would be at 5. So I'm going to sketch that in red just so we can see it better. 1, 2, 3, 4, 5. So it would be right here. And then we know that this graph will cross the y-axis at 2 plus 5, or at 7. So here's our y-intercept. Okay, and we know the general shape of the graph, so it's going to look something like that. Okay, so this is the y-intercept. It is at the point 0, 7. Okay, how about letter B? F of x is equal 2 to the negative x minus 3. So that means, because this x is negative, that means it's going to be a reflection in the y-axis. So we know its general shape. It's going to look something like that. Since it's a reflection, it's going to be shifted down 3 units. So let's start by finding the y-intercept and the horizontal asymptote. The horizontal asymptote will be at the line y equals -3. So I'm going to draw my axes. Oops, make those black. There we go. So I'm going to draw, here's my x-axis, here's my y-axis. Okay, and I'm going to put a horizontal asymptote at -3. Okay, and the next thing I'm going to do is find the y-intercept. Well, the y-intercept will be at k in this case is 1, and c is -3. 1 plus -3 is -2. So my y-intercept is at 0, -2. I know the general shape of the graph, and then it needs to go through this y-intercept and then use the asymptote as a guide as well. And so it would look something like that. All right. And then letter C, f of x equals 3 times 1/2 to the x power. So because this base is between 0 and 1, I know the general shape of the graph is going to be something that's going to be a decreasing function. I know that it's y-intercept. In this case, we could add a +0 onto this function if we wanted to. See that our y-intercept is going to be at the x-axis. So our y-intercept is the x-axis, and then our horizontal asymptote is the x-axis, and then the y-intercept will be at 0, 3 plus 0. 3 plus 0 is 3. So I'm going to put a y-intercept at +3. Okay, here's our y-intercept at 0, 3. Okay, and we know the general shape of the graph. So make sure it goes through that y-intercept and then gets closer and closer and closer to the x-axis without ever touching it. All right, and then our last example, f of x equals -2 to the x plus 1. So this negative out front means it's going to be flipped upside down, and then also it's going to be shifted up 1 unit. So let's start by let's get our axes. Here's the x-axis, here's the y-axis. Our y-intercept is going to be at the line y equals c, so that would be y equals 1. So let's go ahead and draw that horizontal asymptote. And then the y-intercept is at 0, k plus c. Well, k is -1, and -1 plus 1 is 0. So our y-intercept is at the, origin. And this is a function that has flipped upside down, so it's going to look something like that. And there's our y-intercept at 0, 0. All right, so of course you can always use your calculator to check your work, but I want you on your homework to try to first draw these functions without the calculator, and then you can always go back and check it on those, or on the calculator. Okay, so now let's take a look at some models that use some models of exponential functions. So just as a couple of quick examples, let's think about this scenario. The number of water lilies in a pond doubles every week. Okay, so if we have a number of water lilies that are doubling every week, that would definitely be an increasing function. So let's think about an equation that could model the situation. Well, if you think about it, let's say we started with 2 water lilies, okay? Then the next week we would double that, so we'd have 2 times 2. And then the next week we'd double that, so we'd have 2 times 2 times 2. And then the next week after that, we'd double that, so we'd have 2 times 2 times 2 times 2. Okay, and so we can see how this goes on and on. So this would be 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, etc. So one equation that could model the situation would be y equals 2 to the x. Okay, now compare that to the next scenario. Here we have a radioactive substance that has a half-life of 2 hours. What that means is that every 2 hours its radioactivity halves. So an equation that models this situation. Well, again, let's say we had 1/2. Let's just say we have 1/2 of some kind of unit of substance. Then if we take half of that every 2 hours, then we'd have 1/2 times a half. And then the next hour we'd have 1/2 of that, so that would be 1/2 times 1/2 times 1/2, etc. So we can see that we have 1/2 to the first, 1/2 to the second, 1/2 to the third. So one equation that could model this scenario is the function y equals 1/2 to the x power. Now you'll see that that base falls between 0 and 1, and that's what happens when we have a decreasing function. Okay, so let's take a look at a couple of examples of exponential models. This first one says the length L centimeters of a pumpkin plant increases according to the equation L equals 4 times 1.2 to the t. You can see that exponent that variable in the exponent. So this is an exponential function where t is time in days. So the first thing we're going to do is complete this table, giving our answers to 3 significant figures. So you could definitely type this equation into your calculator and use the table function. And when you do, you'd come up with the following values. When t is 0, the output's going to be 4. And then when t is 2, output would be 5.8. And then 8.3, 11.9. Again, this could all be generated on your calculator using the table function. 35.7. So one thing about exponential functions is notice that these values are increasing, and they're increasing at an increasingly rapid pace. Exponential functions grow bigger very quickly. Okay, so now that we have that table, now we're going to draw a graph of L against T going from 0 to 20, let's see, what are we measuring in days? 0 to 20 days, and the length of the plant going from 0 to 100. Now, we do not need to plot every single one of these points. We know the basic shape of an exponential function, so let's just plot a few of them. So let's first of all draw and label our axes. So we're plotting, let's see, L against T. So our length is going to be our vertical axis. And what are we measuring? We're measuring a number of centimeters. And then our horizontal axis will be T. And remember, that was number of days. Number of days. Now, we're counting days from, time is going from 0 to 20. So why don't we count by 2s? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, and then length is 0 to 100. We can count by 10s. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, so let's just plot a few points. We'll start with 0, 4. Which would be right about here. And I'm just going to grab a couple more points. How about the point, let's grab one in the middle. How about this point? 10, 24, 8. So we were counting by 2, 0, 2, 4, 6, 8, 10. And then 24 would be right about there. And then how about the point 1674? So see, 20, 16, 10, 20, 30, 40, 50, 60, 70. Would be right about here. Okay, so you can start to see, again, we don't need to plot every point, but you can see that exponential curve. So then just go ahead and draw a nice smooth curve through those points. And we have our graph. Okay, then letter B says, or letter C, excuse me, says, how long is the pumpkin plant when t is 0? So remember, we find the length by taking 4 times 1.2 to the t power. Well, when t is 0, we can see that that length is going to be 4, okay, because 1.2 to the 0 power is 1, and 4 times 1 is 4. So that is letter C, all right. And then letter D says, how long will the pumpkin plant be after 3 weeks? Remember, 3 weeks is 21 days. So we'll find that length. Oops. Keep grabbing the highlighter. We'll find that length by taking 4 times 1.2 to the 21st power. So grab a calculator, get an answer to 3 significant figures, and that would be 184 centimeters. And then let's look at one more example. It says Hubert invests 3,000 euros in a bank at a rate of 5% per annum. Now remember, that means once per year, compounded yearly. Oh, duh. I guess, and that was kind of redundant. Okay, let Y be the amount he has in the bank after X years. So letter A asks us to draw a graph to represent how much Hubert has in the bank after X years using a scale of 0 to 10 years on the X-axis and 25 to 5,000 euros on the Y-axis. So I'm actually going to do that part last. Let me just go ahead first, though, and write down what that equation would be. Now, you might want to go back and look at your formula chart to find the formula for compound interest. Remember that equation, what we're going to graph is the equation y equals that initial amount, 3,000 times 1 plus the rate is 5%, so 5 over 100, and then that'll be raised to the x power. So that's what we're going to graph, but I'm going to do that after I've actually done parts B and C. So let's go ahead and take a look at letter B. It says, how much will he have after 4 years? So we'll find out how much he has after 4 years by taking 3,000 times 1 plus 5 over 100 and raise that to the 4th power. So grab a calculator and get an answer. And with money, we'll go to 2 decimal places. So that would be 3,646.42 euros. Okay. And then letter C says, how many years is it before Hubert has 4,000 euros in the bank? So that's when we're going to solve the equation. 4,000 is equal to 3,000 times, I'm going to go ahead and simplify this. This is 5/100ths. So I'm just going to call all this 1.05. 1.05, and then we'll raise that to the t power. So here we can let the calculator solve that for us. So punch that in, and when you do, you get an answer of 5.90. I'm going to go ahead and write that to 3 significant figures. So 5.9, almost 6 years it'll take his money to grow from 3,000 to 4,000. Okay, so now that we have a couple of points, let's go ahead and sketch our graphs. Let's go back and do part A. So in part A, let's see, we're going to graph, let's see, our independent axis will be our number of years, and we need those number of years to go from 0 to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is number of years. And then our x-axis, we're measuring how many euros he has. So number of euros. And that needs to go from 2,500 to 5,000. So I guess we could count by 500s. So this could be 3,000, and then 3,500, 4,000, etc. Okay, so let's go ahead and plot a couple points that we know. We know that he initially has 3,000 euros. So we can plot the point 0, 3,000. And then we can also plot, remember we figured out how much money he had after 4 years. After 4 years, he had 3,600 euros, a little more than that. So, let's see, 1, 2, 3, 4, 3,600 would be right about here. Okay, and then since I guess we could plot one more. If we wanted to maybe figure out how much money he would have after 10 years, so that would be 3,000 times 1.05 to the 10th, which turns out to be, approximately 4,886.68 euros. So that point would be right about here. Okay, so all right, so then draw a nice smooth curve. Obviously this is not very accurate, but anyway, we should be able to see it pretty close to an exponential curve. Okay, so your homework is posted in Google Classroom. You can go ahead and get started on that. And if you need my help, be sure and let me know.